Okay, so we're going to revolve around the y-axis. That means this section, this little area, is going to be revolved up out of the paper, down through the paper, and back up to the over here. And we end up with a kind of a ring shape or a donut shape with a flat base. Um, we can try to sketch it. This one is challenging. So here's my ring in perspective. And here's the inside. Okay. And then it has this parabola shape like this. And this one is hard to draw cleanly on a two-dimensional sheet of paper. Like I said, three-dimensional object, think of it sitting flat on the paper with a little parabola sitting on top of a ring around this way. So a rounded shape. So our first thought should be, when we're finding the volume of this kind of shape, we should think about the cross sections, the discs and the washers that we were using last time. So if I wanted to use a washer, since there's a gap in the middle here, this is where the parabola would end up on the other side. So if I rotated it through, it would end up back over here as we rotated. So there's this gap in the middle. So if I was going to use a method from last time, we would need to use washers to make slices this way and across there as well. But in order to do it this way, we have to find the distance between these two legs of the parabola. So that problem, finding the distance between that edge and that edge, based on how high we are, that's actually a surprisingly difficult problem. So we would have to solve this equation for x. So probably we would have to use the quadratic formula. And if we had a more complicated function like a cubic or a square root thrown in there, or even something more complicated like an exponential function like we're going to be dealing with a little later on, that method would not work at all. We wouldn't be able to solve this for x. So this idea of using washers is not going to be our best option. It's going to end up being too hard. So instead, what we're going to do is make vertical slices like this. And think for a second, looked like my connection was a little unstable there. Looks like it's fine again. So think about what happens when you revolve this vertical segment, this slice, around the y-axis. So what kind of shape is it going to form? Any ideas?
Would it be a cone shape?
So a cone, so something that tapers to a peak. Let's see. This kind of thing?
Yeah, maybe not quite that sharp though.
Okay.
More like a bullet.
What word did you use?
A bullet?
Oh, a bullet. Okay. So like this gentle taper. I get what you're saying. Um, but what I'm doing is I'm actually just making a vertical slice. So like this line segment here. It doesn't have any curve at all. It's just straight up and down.
Oh, okay. I thought it was that whole piece to the outside.
Okay. Yeah, just this one segment.
Would it be a cylinder?
Yes. So we're going to make a cylinder when we rotate this around. So let's see if I can sketch it. So here's the bottom of the cylinder. Here's the top of the cylinder. And here's the back. Okay, starting to get a little messy, but we make these cylinder shapes as we do our slices. So now let's come down here where it's a little cleaner still and take a look at our cylindrical shells. So I've taken this cylinder and I've pulled it out here where we can look at it a little bit better and think about it. Because what we're going to be doing is we're going to take the volumes of our little cylinder slices, our cylindrical shells. So they have just a little bit of thickness. That's why we call it a shell. And we're going to add up all of the volumes for our little cylinders and try to use that to get the volume of the whole three-dimensional shape. So here's what I'm going to do. I've kind of already drawn it out. Instead of trying to find the volume of this cylindrical shell, which seems a little bit hard, at least to me, I'm going to cut my cylinder. So imagine I've just cut it vertically on one of the sides and then flatten it out. And what we get instead of a cylinder is actually just a rectangular prism. And the volume of a rectangular prism is really easy to find. It's, well, I said length times width. We also need the height, of course, since it's three-dimensional. So let's see if we can work out the length, width, and height of this cylindrical shell from our picture up here. So the first question, and this is, I think, the hardest question, is what is the length? So when I make my slice and I flatten it out, what's the length?
Wouldn't it be the height of the cylinder?
There was another response too. I don't know who was talking. Was someone else saying something? No? Okay. So you said the height. The height of this cylinder, we will definitely need over here. But what about the length? So when I make my vertical slice and I flatten it out, what's this flat length?
The circumference?
Right, it's the circumference of the cylinder. So what is the circumference here? We have to think about it. We have to think back to where it came from in the graph. So we went out along the x-axis to a certain point here. Let's label it x. And this distance from the center to x became the radius of my cylinder. So the circumference we get by multiplying by 2 pi x. Okay, so let's fill that in over here. The length is 2 pi x. And the width here, I'm just going to tell you what that is. So like before, when we were making little rectangles in Riemann sums, we called the width of our rectangles delta x, because it's going to be a really small distance that gets smaller and smaller as we use more and more cylindrical shells in this case. So we have just the symbol delta x. And finally, what about the height? What's the height of my cylinder? What's the height?
One.
I guess it does look like it's about 1. So that's good. But what I'm asking for is this here. So the height of the curve is given by this function. And we can try to fit it in somewhere. So it's some function, and in this particular problem, it's minus x squared plus 4x minus 3. And I think down here, I'm just going to write f of x, because this could be different depending on your particular problem. Okay, so if we wanted, we could make lots of cylindrical shells. We could make lots of slices in our picture. Maybe we could do 10 slices, and we could get an estimate for the volume. We could add more slices. We could do 20 or 50, whatever, and get better and better approximations, just like with Riemann sums and integrals. And if we want the exact volume, we need to take the number of shells to infinity. So if you actually work through all of the details of the math, you would have a limit of a sum, a limit of a sigma, and it becomes an integral. So when you add an infinite number of shells, it becomes an integral. And here's what it looks like. I've written it out in words. We have 2 pi x up here for my volume. X was the shell radius, so that's what I wrote here. And then we have the shell height. That was my function. And then delta x, as we add an infinite number of shells, becomes dx. So we're not going to bother, like you did in Calculus 1, trying to use an approximation when you first learned about Riemann sums. We're just going to go straight to the integral in practice. But are there any questions before we actually do one of these integrals? Any questions about the geometry? Okay, I guess everyone's pretty comfortable. The integral looks pretty similar to what we've been doing the last week or so. So let me write it down again, so v equals the integral from a to b of 2 pi times the shell radius times the shell height dx, and then we add up all of the little tiny volumes to get the total volume. So it's like we're adding up areas almost to get a volume if we add up an infinite number of areas. It's not exactly the mathematics of what's going on, but it's a good intuition. We have like flat slices that add up to a three-dimensional object. Okay, so back to the picture, we need our limits of integration. It's gotten a little bit messy, but we can read it off from my graph that I made. The shape starts at 1 and it ends at 3, this original region that we were looking at. So those will be our limits of integration in this problem. And then 2 pi, the shell radius, we know to be x. Let's see, maybe I'll leave parentheses around that so that it looks the same. And then the shell height was the function minus x squared plus 4x minus 3. Okay. And now it's just a matter of doing the integral. We have a constant that we can move out to the front, and we also need to multiply through by x. So distribute the x into this set of parentheses. Okay, so everything increases in power. We have a minus x cubed plus 4x squared minus 3x. And then we use the power rule to get our integral. What's a good antiderivative? Anyone?
Negative 1/4 x to the fourth.
Good. What's next?
Plus 4/3 x cubed
Okay.
minus 3/2 x squared.
Okay, good. And then we need our limits of integration, 1 to 3. And then we'll just plug in and find the difference. This is another one of those problems where when you work it out, there are lots of fractions to deal with. Maybe we can write out some of it. So maybe leave your 2 pi on the outside and then plug in 3, so minus 1/4 times 3 to the 4th power plus 4/3 times 3 cubed minus 3 halves. Three squared. Okay, so that takes care of the upper limit. Then we subtract, plug in 1. 1 to a power is going to give you a 1 in all of these places. So we don't actually have to write all of that out. We just need the fractions. Minus 1/4 plus 4/3 minus 3/2. Okay, so doing this by hand, the next step would be to do all these powers of 3. So 3 to the 4th, 3 cubed, 3 squared, and then combine your fractions, finding a common denominator, I guess you would need 12. I think I'm just going to tell you the final answer at this point is 8 pi over 3. So once you finish reducing, this is what it comes out to. Okay, so any questions over this integral? Okay. I guess everyone's happy with the integral. Are there any questions about the process of using cylindrical shells and setting up a problem? Okay, guess not. So we will move on to another example, so where we have to start from scratch again and use cylindrical shells. Now we're going to look at the region bounded by y equals the square root of x, the line x equals 4, and the x-axis, and it's going to be revolved about the line x equals minus 1. And we want to find the volume of the generated solid. So the first step, just like last time, is to start sketching and graphing. And we'll just start with the square root of x. So this looks like a sideways parabola, or the upper half of one. We can plot in a few points to get a rough picture. If you plug in 0, you get 0. If you plug in 1, you get 1. And if you plug in 4, you get 2. So something like this. And we know we can't plug in negative numbers because then we would get something imaginary. So we don't have to worry about anything over on the left side of the x-axis. Okay, so there is our curve, y equals square root of x. Now let's put in our two vertical lines, x equals 4, 3, 4. Okay, and the x-axis is the other bound. That means we're looking at this triangular-like shape here. And we're going to revolve it around another vertical line, x equals minus 1. Maybe I'll do this one as a dotted line. Okay, so this is the basic geometry. Now we have to think about what happens when we revolve. So this is going to be revolved around this way to form a three-dimensional ring shape again. This one isn't rounded like in the last example. It has an edge here, a straight edge. And you can kind of just imagine if it goes out of the paper and then back through, we want to think maybe about what kind of shape we have. So we started 1 away from this line. That means we're going to end up back here. And then you can figure out where all these points are. This point was 2 away from minus 1. So go 2 the other direction. This point was 5 away from minus 1. So go 5 in the other direction over here. And we can get a rough idea So this will come out of the paper, making a three-dimensional shape, and then it's going to hit the paper again right here. It'll look like that. And then it'll go back down through the paper and come back to meet this again. Okay, so should we use discs or shells or washers? Well, since this is in the section about shells, maybe you can guess correctly which one. Discs would work this way, but you can see there's a gap, so a disc wouldn't be exactly right. We would have to use washers like this. So we would have to find the distance between this square root of x curve and this vertical line. Let's see, and it sounds like someone's microphone is on. So make sure you're muted. Let's see. I guess there isn't any more noise. We should be good. But just like before in the last problem, finding this distance is not the easiest thing to do. We could do it. It's much easier if you just slice vertically. So if you just slice from the top of the curve y equals x squared down to the x-axis, because, well, this is the point x, and, well, x, maybe x0, and this is x square root of x. The height is square root of x. So this is much easier. We don't have to solve anything. Everything's already given to us. So we're going to make our slices vertically, and this is going to form cylindrical shells. Down here, I'm going to write the formula for our integral. Just like we had it before. So the integral from a to b of 2 pi times the shell height, or I think I did this in the opposite order. We also need the shell radius, and then dx. Okay, so the first thing, at least the way I've written it, what is the shell height? What's the height of my slice?
The square root of x.
Right. So we don't have to think too hard about that one. It's just given by our function. What about the shell radius? And remember, we're revolving around this line. So what's the distance between this point and this one? Is it x?
X minus 1.
Okay, x minus 1, you're very close. Because if we're finding the distance between 2 points, we subtract. So x minus whatever this value is. But keep in mind that this is a -1. So we have to subtract -1, like this. So we actually end up adding 1. So remember, thinking back to number lines, if you want the distance between A and B, then the distance is B minus A. And that's why we have this double negative, why we're subtracting -1. Okay, and one more thing to fill in. We need our limits of integration. So we need to figure out what these limits are.
0 and 4.
0 to 4, good. And these were given to us in the problem. You don't actually have to do geometry for them because we know our bounds are x equals 4 and the x-axis x equals 0. Okay, so let's work through this integral. The first thing you'll want to do is distribute the square root. Well, maybe rewrite that as a positive first, in reality. And you also want to think of the square root as x to the 1/2, because we're going to need the power rule in a few minutes. And this becomes x plus 1. And now I need to move to a new page. But I'll leave that there for a second in case any of you are writing. Okay, so I'll write that last step down again. We're integrating from 0 to 4, and then 2 pi x to the 1/2 x plus 1 dx. And your next step will be to probably pull the 2 pi to the front, since it's a constant, and then distribute x to the 1/2 into the parentheses. So 1/2 plus 1 gives us x to the 3/2, and then times 1 gives us another x to the 1/2. And once we do that, our integral is now written in a way that lets us use the power rule. So what is a good antiderivative?
Would it be 5 x to the 5/2?
Mhm.
I'm sorry, 2/5 x to the 5/2.
Good, yeah. And then do the same thing, increase by 1, divide by the new power. So this becomes 3/2 in the exponent, and then you flip the fraction and multiply by 2/3. Okay, so now we're done with the calculus. We just have to plug in our limits and subtract. Okay, so we need 2/5 times 4 to the 5/2 plus 2/3 times 4 to the 3/2 power. And then we plug in 0 in both of these places, but when you plug in 0, you're just going to get 0 in both of those. So we'll end up with nothing to do for this guy. We can save ourselves some writing. And maybe we'll think through all of the details here at the end on this one. So what is 4 to the 5/2? Well, think about what 5/2 means in the exponent. It means we're raising to the 5th power and then taking a square root. And for this one, it's easier to think about, 4 to the 1/2, because that's just 2. And then raise it to the 5th power. So bring down your fraction, take the square root, you get to raise it to the 5th power, and you get 32. Okay, and now do the same thing here. 4 to the 1/2 is 2, and then cube it to get 8. So this one we can actually finish out by hand. You would need to find a common denominator. Maybe I'll let you do the common denominator part and just write the answer. Some of these numbers get a little large. And we end up with 544 over 15. Oh, and a pi, 544 pi over 15. Okay, any questions over this example? Okay, I guess we'll just move on then. We'll do one more example from this section, a different kind of revolution. We're going to look at the same region bounded by y equals the square root of x equals 4, and the x-axis, but now we're going to be revolving around the x-axis. This is a typo. And then I want to find the volume of the resulting solid. So we're looking at the same region. I'll go ahead and sketch it again. So here's the square root function. Plot in a few points and then sketch. And then we have our vertical line at x equals 4. And then the x-axis. So same region, but now we're going to revolve around this way. So when you revolve around this way, you'll end up getting the same kind of shape down here, so that we end up with something that truly looks like a parabola after you rotate around. Okay, so we have to decide what method to use. For this particular revolution, volume of revolution, we could make slices this way and then look at disks. But what I want to do for this one is actually compare what would happen if we did shells again. So I want to slice this way horizontally, and this is going to make cylinders again. I can try to draw one here. Okay. So I want to make cylinders like this one, and then try to do the volume. But now we're going to integrate with respect to y. Because I'm slicing across this way, that means I'm integrating my slices. I'm adding up my slices vertically. So let me go ahead and write down the formula down here so we can see what we're missing and what we need to fill in. So we still have 2 pi times the shell radius times the shell height. But now we're integrating with respect to y. So I'll put a dy here. So the first thing to do, I guess, is to think about the radius. And the radius of my shell is going to be this way. So what's the radius of this particular shell that I drew? So if I mark this as x, what is the radius? Well, it's just the height up to the function, right? It's the square root of x. What about the height? This is where it starts to get a little bit more complicated. I need to find the distance between x equals 4 and the x coordinate here. And maybe you've also noticed a problem with my radius, because I'm integrating with respect to y, and here my radius is written in terms of x. So I'll have to rearrange this as well. So let's find some blank space. Y equals the square root of x. We'll have to solve this for x, or we'll have to rewrite it. We're actually not solving for x. Solving for y. So the radius is equal to y. But now we have to find this horizontal distance also in terms of y. So here I've written x, but I need this distance here, not this distance here. Any ideas? So remember, y equals the square root of x. So if I want to rewrite this in terms of x, if I want to solve for x, I would have to square both sides. So x is equal to y squared. And this is more like what I need, because instead of x, I need something with a y in it. Okay. And now I need the distance between 4, x equals 4, and y squared. So this is going to come out to 4 minus this point, or this coordinate. 4 minus y squared. Okay, so now finally we found our radius and our height both in terms of y, and we can plug in. Here, I guess I've run over a minute or two. The radius is y. The height is 4 minus y squared. Yeah, if you need to leave, that's fine. I'll post these last few minutes of the class on Blackboard if you need to come back and look at it. Okay, so here's my integral. My limits of integration are my y limits. So we start at 0 and go up to 2. Okay, so this is the integral I need to do to find the volume. Since we don't have any extra time, I'll let you work through the details and then you can check your answer. It should come out to 8 pi. Okay, and for those of you left, let me just make one comment here at the end. This way of thinking about things was, I think, kind of challenging. And the reason why it was so hard and why it was harder than it needed to be is because I made the wrong choice. I really shouldn't have used shells on this problem. It would have been much easier to do the other way, to do disks. You wouldn't have had to do any of this extra geometry kind of stuff. You could have just written down your integral really quickly and then done the calculus and finished it off. So when you're working through your homework and when it comes to an exam, make sure you think a little bit before you get started about what method should be easier. Okay? And then working through the assignment will help you get an idea of what I mean by that. Are there any questions?